In this lesson, we're going to be talking about executable types for Unix-like systems. In the early days of Unix, in the early 1970s, there was one executable format that was called a.out. And actually, compilers would generate a file called a.out if you didn't actually specify an output file. The compiler would generate a file called a.out when it compiled a program. Now, the a.out executable format has actually been superseded a couple of times. It was eventually replaced with the Common Object File Format, or COFF, C-O-F-F. Now, interestingly, the COFF executable file format was the basis for the Windows Portable Executable File Format. So Windows actually used this common object file format that was common under Unix for a while. It used that as the basis for its portable executable format. These days, though, under Unix-like systems, primarily Linux, you will see an executable and linkable format, which is typically called ELF. So I've got a program here called WordList. And you can see there's the file WordList, and let me do a file on it. And you can see this is a 32-bit LSB executable, and it says ELF, and it's for an Intel 8386. And again, it's 32 bits, so it's not a 64-bit. And it's also not compiled for a higher level CPU, so we're only using instructions from the Intel 8386 instruction set. So none of the instructions that have come in subsequent processors. So there's ways of looking at the different portions of this executable under Linux, and there's a program called readelf that works really well at pulling WordList apart. And again, this is a command line program, so you have to know what the different switches are. And let me just bring those up here so we can see the help for this readelf program. Here's all of the different switches that you would need to know to run this program. I'm just going to show a couple of examples here, so that we can actually take a look at a Unix program, or in this case, a Linux program, and see what's going on. So I'm pulling apart the section headers for this particular program. You can see there are 31 section headers, and it says it starts at offset 0x, and the X indicates that it's a hexadecimal number that follows, and that number is 1168. So that's the offset, that's the memory offset where all of these headers start. And you can see, particularly compared to the Windows Portable Executable format, there's a lot of different sections in this ELF formatted program. Now, the interesting thing about this is in the 8th column, there's a set of flags, and at the bottom, it says what the key for those different flags are. So we could take a look at, for example, the text segment, which is line 13, and it says AX, which means that's a segment that needs to be allocated, and it's one that can be executed. Now, why would we want to have execute flags on these different segments? Well, the reason is, if you've got a segment where there's data, you don't want that segment to be executed or executable, because that opens the door to things like buffer overflows, where we have the case where arbitrary code could be executed if a program could be executed in such a way as to trigger a vulnerability and trigger a buffer overflow. We don't want data segments in memory to be able to be executed. So you can see that these different sections actually have flags, which helps the operating system determine how it's going to handle each of these particular segments. So we've got some other ones here. I notice there is a few sections here that actually have the write flag turned on. And again, that's useful because not all segments need to be written to. So a text segment or a text section, we shouldn't be writing to that because that's the code that we want to execute, and we don't want the code changing itself or having somebody else change it as it's running. So we want to be able to just put that text segment in place and not flag it as writable at all. It needs to be allocated in memory so that there's some space for that text segment to live, but we don't want to be able to write to it once it's sitting in memory. So let's take a look at another thing here. We're going to look at relocatable sections, and I'm going to use the word list program again. And we've got some relocation sections that are noted here. You can see that there's a symbol name, which is the name that the linker used to point to a different function or a particular function. So you can see the different sections that are relocatable in this particular word list program. Now I can do, and I'm going to use word list again. So I'm going to list the segments here. You can see there are 9 program headers, and at the bottom here, it's got the section to segment mapping. You've got the different sections on the right-hand side that map to the different segments on the left-hand side. So we've got a program called readelf, and that will help you to pull a program apart and figure out the different sections that are in the program and figure out where the data segment is and where the text segment is and where all of the different sections of the program actually are. Now, in terms of a running program, we could actually take a look at, actually going to do this, and we're going to look in the proc file system. And the proc file system is where process data is stored. It's a virtual file system that doesn't really live anywhere. It's just information about the different processes that are stored in a portion of the running file system, or they appear to be stored in a portion of the running file system so that you can access the data. So let's just take a look at process 1. And that would be the init process. And I'm going to open up the maps file. Now, there's a file in this particular virtual file system for every process, and it's called maps, and it tells where all of the memory segments for the program are and what they are mapped to. And you can see they are linked to different libraries. So you can see the .so extension, those are library files. So we've got the libnss files, and down lower we've got the libc, so that's the standard C libraries. Now, the ones that don't have a file associated with them actually belong to the program itself. And you can also see down at the bottom, the very bottom, you can see where the heap is and where the stack is. So we've got a way to not only look at the different segments of a static program, meaning one that's just sitting on the disk not executing, but we've also got a pretty easy way of looking at the different segments and where they are in memory of a program that's actually running and executing at the time that we are looking at it. So again, primarily you're going to be running into, on the Linux side or Unix-like operating side, you're going to run into this executable and linkable format, or ELF format. Now, Macintosh actually has its own format. Even though it's Unix-like, it's got its own executable file format called mock-O. And the reason it's called mock-O is because about a dozen years ago, when they rebuilt the Mac OS to take into account the acquisition of the company Next, they actually used the Unix underpinnings that were part of the Next operating system, and it used this thing called a mock kernel. So the operating system for Mac OS is actually a mock kernel, meaning it's Unix-like in nature, and Mach kernel was a very, very small kernel. It was designed to be small and fast. So Mac OS actually has its own executable file format called Mach-O, but when you're running into Linux or other types of Unix-like operating systems, you're probably going to be running into this ELF file format.